Hello and welcome to G Fun Facts Online. For centuries, we've looked up at the stars as silent, distant points of light. We saw their brightness, their color, but their inner workings, the very hearts that define their lives and spectacular deaths, were completely hidden. It was like we were looking at shadows on a cosmic cave wall. But what if we could do more than just see? What if we could listen? Today, we're tuning into the cosmic symphony. We're exploring Astro-Seismology, the science that lets us hear the heartbeat of the stars, revealing the secrets of their final, dramatic moments. At its core, Astro-Seismology is the study of stellar oscillations. You see, stars aren't static, perfect spheres. They are giant, roiling balls of hot gas that vibrate and resonate. Just like a massive musical instrument, like a bell, a star's size and internal structure determine the specific tones it can produce. These vibrations cause tiny, subtle changes in the star's brightness over time. By using incredibly sensitive telescopes, we can detect these fluctuations. The frequencies of these vibrations, the star's unique set of notes, tell us a phenomenal amount about what's going on deep inside. We can deduce its density, its temperature, its chemical makeup, and even its precise age. It's a bit like how geologists use seismic waves from an earthquake to map out the Earth's core. But we're doing it for a sun that might be millions of light years away. This stellar music is a complex harmony, mainly composed of two types of waves. First, you have what are called pressure modes, or P modes. Think of these as sound waves, acoustic waves, that travel through the star. They are high-frequency vibrations, with cycles ranging from minutes to hours, generated by the churning, turbulent gas in the star's outer layers. P modes are fantastic for measuring a star's fundamental properties, like its mass and radius, because they are most sensitive to the conditions near the surface. The second type are gravity modes, or G modes. These are much slower, lower-frequency waves. To understand them, imagine a blob of gas in the star's stable interior that gets displaced upwards. It's now in a less dense region, so it's heavier than its new surroundings, and it sinks back down. But it overshoots its original position, entering a denser region, which makes it buoyant, and it rises again. This up and down bobbing motion, driven by the force of buoyancy, creates a wave, a gravity wave. These waves are confined to the deep, radiative interior of a star, and they are notoriously difficult to detect from the surface. But finding them is the holy grail for astronomers. Why? Because G modes come directly from the nuclear burning core, the very engine room of the star. They carry direct information about the core's composition and, crucially, how fast it's spinning. The intricate dance between these P modes and G modes creates a unique acoustic fingerprint for every single star. Its internal structure acts as a resonant cavity, deciding which frequencies can ring out and which are silenced. By carefully analyzing this frequency spectrum, astronomers can build a detailed model of the star's interior, just as a trained musician can identify an instrument simply by the sound it makes. This technique becomes incredibly powerful when we turn our attention to stars nearing the end of their lives. As stars run out of fuel, they undergo huge transformations, either swelling up into red giants or collapsing into dense white dwarfs. Astro-Seismology allows us to peel back the layers on these cosmic elders and witness their final acts. Let's start with the swollen hearts of red giants. When a star like our Sun burns through all the hydrogen in its core, it doesn't just switch off. The core, now mostly inert helium, contracts under gravity and heats up. This intense heat ignites the hydrogen in a shell surrounding the core. This shell-burning phase is incredibly powerful, pumping up the star's outer layers and causing it to expand to hundreds of times its original size. It cools down as it expands, turning it into what we call a red giant. These giants are fantastic targets because their oscillations are much larger in amplitude and have longer periods than those of a star like our Sun, making them much easier to detect. One of the biggest breakthroughs in red giant astroseismology has been learning to tell different types of red giants apart. For instance, a star on the red giant branch is in that first stage, burning hydrogen in a shell. But a red clump giant has reached a later stage, where its core has become hot and dense enough to ignite helium. From the outside, these two types of stars can look almost identical in brightness and temperature. For a long time, it was a major puzzle for astronomers. Astro-Seismology solved it. The key was the detection of something called mixed modes. Picture the P modes as sound waves trapped near the surface, and the G modes as gravity waves trapped deep in the core. In a red giant, the internal structure is just right for these two separate wave regions to talk to each other. The P modes can tunnel into the core and couple with the G modes, picking up sensitive information about the core's conditions before traveling back to the surface. It's like sending a spy deep behind enemy lines and having them report back. Since G modes are sensitive to the core's density and composition, the spacing between the frequencies of these mixed modes is different depending on what the core is doing. A star with an inert helium core has a different heartbeat than one with a core actively burning helium. This subtle difference in their rhythm allows astronomers to definitively identify their evolutionary stage. This stunningly precise diagnostic tool has also revealed something else astonishing. The cores of red giants often spin much faster than their outer layers. This tells us that as the core contracts, it spins up, just like an ice skater pulling in their arms to spin faster. The outer layers, which are expanding, don't feel this effect as strongly. This creates a huge difference in rotation speed, and understanding how the star's layers break and exchange this rotational energy is crucial for our models of how stars evolve, and even for predicting the properties of the remnants they leave behind, like black holes and neutron stars. Now, what happens after the red giant phase? For a star like our Sun, after it gently sheds its bloated outer layers in a beautiful glowing structure called a planetary nebula, all that's left behind is its hot, dense core, a white dwarf. These are the fossils of stars. They pack a mass comparable to our Sun into a volume roughly the size of the Earth. A teaspoon of white dwarf material would weigh several tons. As these stellar remnants cool down over billions of years, they pass through certain temperature ranges called instability strips. Here, they become pulsationally unstable and start to vibrate. These pulsating white dwarfs are some of the most fascinating objects we can study. Their vibrations are almost exclusively G modes, those deep, core-probing waves we talked about, with periods ranging from a few minutes to about half an hour. The pulsation mechanism is often something called the kappa mechanism, which acts like a tiny heat engine. In a specific layer of the star's atmosphere, elements like hydrogen or helium are partially ionized. When this layer gets compressed by a wave, it becomes more opaque and traps heat. This trapped heat increases the pressure, pushing the layer back outwards. As it expands, it cools and becomes more transparent, releasing the heat, and falls back inwards to repeat the cycle. This drives the pulsations. And by studying these G-mode pulsations, astronomers have confirmed a theory that sounds like pure science fiction. Stellar crystallization. Theory predicted that, as a white dwarf cools, the immense pressure should force the carbon and oxygen in its core to arrange themselves into a rigid crystal lattice. In essence, the heart of the star turns into a giant, cosmic diamond. This transition from a fluid plasma to a solid crystal is a phase change, just like water freezing into ice. And just like freezing water, it releases a significant amount of latent heat. This extra energy source messes with the star's cooling schedule, slowing it down slightly. The pulsations act as our probe. Their periods are determined by the travel time of waves through the star. A solid core changes that travel time compared to a liquid core. By tracking the gradual changes in pulsation periods over years, astronomers can actually map the growing size of the crystal core inside the white dwarf. It's an incredible feat of indirect observation confirming that the universe is filled with planet-sized diamonds. White dwarf astroseismology is also turning these dead stars into the most accurate clocks in the universe. We know that white dwarfs cool at a predictable rate, so their temperature gives us a rough estimate of their age. But by using Astro-Seismology to precisely measure the white dwarf's mass and internal structure, we can refine these age estimates with incredible accuracy. This allows us to date star clusters, streams of stars from cannibalized galaxies, and even the age of our galactic disk itself, helping us piece together the formation history of the Milky Way. For decades, the true potential of this field was held back by a simple problem. Our planet, Earth's turbulent atmosphere, blurs starlight, and the constant cycle of day and night means we can never get the long, uninterrupted streams of data needed to detect these tiny stellar flickers. The revolution came when we put telescopes in space. The absolute game changer was NASA's Kepler Space Telescope, launched in 2009. Kepler's primary mission was to find exoplanets by staring at a single patch of sky for 4 straight years, measuring the brightness of over 150,000 stars with mind-boggling precision. This fire hose of perfect data was a dream come true for astroseismologists. Kepler's unblinking, 4-year-long stare gave us light curves, graphs of brightness over time, of unprecedented quality. They were so clean and so long that the subtle frequencies of stellar oscillations, previously buried in instrumental and atmospheric noise, stood out like clear musical notes. Kepler ushered in a golden age for the field, increasing the number of stars with detected oscillations by a factor of nearly 100. Many of the incredible discoveries about red giants and white dwarfs we've just talked about were only possible because of Kepler's data. Its successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, is taking the next step. While Kepler gave us a deep, narrow look at one part of the sky, TESS is giving us a broad all-sky survey. It's creating a map of stellar heartbeats across the entire celestial sphere. This is crucial for galactic archaeology, using the ages of stars all over the galaxy to reconstruct its history. TESS's observations of red giants are proving to be as good as Kepler's for this purpose, but for a much larger, more diverse sample of stars. And TESS is allowing us to combine exoplanet science with astroseismology like never before. When we find a planet, we can now also study its host star's vibrations. This lets us determine the precise age of the star and, by extension, the age of its entire planetary system. We can finally build complete family portraits of other solar systems. And the future of this field is even more exciting. The upcoming Plato mission from the European Space Agency is being designed specifically for this synergy. Plato will find Earth-like planets in the habitable zones of Sun-like stars, and by performing astroseismology on those same stars, it will tell us their age with an accuracy of 10%. Knowing the age of a planetary system is the missing piece of the puzzle. It tells us if a planet has had enough time for something interesting, like life, to potentially develop. Scientists are also pushing the boundaries to study even more exotic pulsating objects, like the exposed helium-burning cores of red giants called subdwarf B stars. But the ultimate prize, the most challenging observation, would be detecting oscillations in a neutron star, the ultra-dense remnant of a massive supernova. Hearing the vibrations of a neutron star would be a direct probe of matter at densities and pressures we can never hope to replicate on Earth. It would open a window into the most extreme physics in the universe. Astro-Seismology has fundamentally changed our relationship with the stars. They are no longer just silent, static lights in the night sky. They are dynamic, evolving beings with rich, complex inner lives. By learning to listen to their heartbeats, we are not just learning about the stars themselves, but about our own place in the universe. The very elements that make up our world and our bodies were forged inside stars that lived and died billions of years ago. Understanding their life cycles is to understand our own cosmic story. The rhythms we hear from distant, dying stars are a preview of our own sun's future. In a few billion years, it too will become a red giant, and then a cooling, crystallizing white dwarf. It's a powerful reminder that we are part of this grand, ongoing cosmic symphony. From silent shadows to a resonant chorus, the music of the stars is the story of where we came from and where our star is going. It's the story of cosmic creation and destruction, written in frequencies and vibrations, and for the first time, we finally have the ears to listen. Thanks for tuning in to G Fun Facts Online.